into a polymer, or that polysaccharide. Good.
Because each individual like pentagon is a monosaccharide, and when you add multiple, it becomes a poly.
Exactly right. So for those of you who couldn't hear that, each of these pentagons, I almost said pentagrams, it's not that, each of these pentagons is a monosaccharide, and we add them together to create a polysaccharide. Yep, exactly right. And because we're sticking things together, that is a synthesis reaction or dehydration synthesis. Okay? Are you guys okay with this? Okay, let it I guess simmer for a little bit, and then when we review at the end of class, if you want to go over this again, we can definitely do that. Okay? Yeah.
Can you like draw this diagram?
No, I won't ask you to diagram a glucose molecule. Yeah. You should be prepared to diagram atoms, show ionization type stuff. All right, so after we talked about the carbohydrates, we talked about another class of molecules, and those were the lipids, right, or our fats. This is kind of a trick question, right? So what is the monomer of dietary lipids? Triglycerides. There isn't one, right? There isn't a monomer. However, when we were connecting our glycerol molecule to a fatty acid chain, now I won't draw the hydrogens onto that. We did dehydration synthesis, right, between this carbon and this carbon. Oh, I have those on the wrong side. So it should look like that. So we did a dehydration synthesis reaction between glycerol and our fatty acid, and we did that by taking OH and H off, so that there was a bond between carbon, oxygen, and carbon. It looked very much like our glycosidic linkage. What was the name of that bond?
Ester bond.
Ester bond, yep. Like the woman from the Old Testament is an ester bond, or an ester linkage. So I'm going to use linkage and bond synonymously. Okay, so if I say linkage, bond is a synonym. If I say bond, linkage is a synonym. You could see it either way on the exam. Okay, now what was the function of our lipids? And there were a bunch of them. So just start calling them out.
Long-term energy storage.
Okay, long-term energy storage. Now, let's clarify that one really quickly. Long-term energy storage specifically for animals. Okay? I want to talk just briefly about the differences between plants and animals storing energy. So long-term energy storage. Okay, what else? Communication. Okay? Insulation, love it. And then cell membranes, somebody said. Cell membranes. Now, our triglycerides are specifically for long-term energy storage, insulation, and then also cushioning. Our bodies are really, really good at storing fats. So, for us, long-term energy storage is accomplished in the form of triglycerides, and it's stored in a specific tissue called adipose tissue. Now, over evolutionary time, our bodies have been really, really good at holding on to and storing these fats. Because if you think about the way that Homo sapiens evolved back on the savannas of Africa, our meals were few and far between. And when we'd come across some meal, we would gorge ourselves and just eat as much of it as we could and then store that for as long as we could because we didn't know when our next meal would be coming along. Now plants are fundamentally different. Plants, first of all, don't have to move around and they have a constant supply of energy. What that allows them to do is be a little bit more liberal with how they store energy. Energy is stored in plants using carbohydrates. So think about like a potato tuber, potato, the root, or a carrot. They have these really, really large, bulky organs that they use for storing energy. But that's okay, because they don't have to like pull them up out of the ground and hike off, right? They can leave them under the ground. So having a lot of space to store energy is okay for plants. Terrible idea for us. If we had to store all of our energy in the form of carbohydrates, because it's such a large, bulky molecule, we would weigh an enormous amount. Consequently, we've developed tissues, these adipose tissues, that store twice the amount of energy as a carbohydrate in the same gram of space, or the same gram of molecule. It's okay for plants to be really inefficient at storage space. It's not okay for us to be inefficient at storage space because we have to move around. Does that difference make sense? Okay, very good. So let's move on to two other types of fats. Let's talk about cell membranes, and I think I have, yeah, cell membranes and then also communication. So one of the cool things that all cells have is a plasma membrane. And this plasma membrane is important because it accomplishes a task of selective permeability. Cells maintain homeostasis, which means that we need to be selective about the kinds of things that come into the cell and the kinds of things that leave the cell. Largely that's accomplished by a particular type of fat called a phospholipid. So phospholipids look very similar to our triglycerides. And instead of drawing it horizontally, I'm going to draw a phospholipid vertically. So phospholipids consist of a glycerol molecule, like this, and they're connected to two fatty acid chains. And I'm just going to write fatty acid. To the glycerol molecule. But then, what differentiates them from the triglycerides is that they're attached to, right here on this third carbon, a large phosphate group, hence the name phospholipids. Now phosphate is a really important group for us biologically. We use this for energy, and we use it for energy for the same reason that cell membranes use it for membrane integrity and selective permeability. It carries a negative charge. Now that's a really important characteristic. So if you were to take a whole bunch of phospholipids and throw them together inside water, they just spontaneously form a membrane, and that membrane is referred to as a micelle, and it looks something like this. All of the phosphate heads, and we're going to call this the head, all of the phosphate heads line up really close together, like this. And then those fatty acid tails also line up really close together, like this. All on the same side. But they don't just stop there. We get another layer of phospholipids that lines up below that first line. And the fatty acid tails stick up. Like that. And this membrane will just create a complete bubble. Now, think about the bipolarity of this membrane. We have this section that is chemically very, very different than either this or that. Triglycerides, if we're to back up just a second, triglycerides had 3 long fatty acid chains. Did those dissolve well or poorly in water? Very poorly, right? Triglycerides don't dissolve in water at all. It's because these don't carry a charge. They're all just happy and content. That's considered a hydrophobic substance, right? So that's true for the center of this membrane as well. This membrane center is hydrophobic. But these heads carry a charge, and they carry a negative charge, which means that they could potentially interact well with water, right? There was a part of the water that carried a partial positive charge. What was that? Oxygen or hydrogen? 50-50 chance.
Hydrogen.
Hydrogen, yeah, exactly right. It's hydrogen. So the phosphate heads are going to interact really, really well with that partial charge of positive for the hydrogen. So these are considered hydrophilic. Now think about how cool this is. Because this is hydrophobic, let's say this is the outside of the cell and this is the inside. Because they're hydrophobic, nothing that carries a charge is going to be able to cross this barrier. Nothing that carries a charge is going to be able to cross that barrier unless our cell actively allows it in using some other molecules. So, could water pass freely across this membrane? No. No, it couldn't. It's close to yes. It's no. So, and it's no because does water carry a charge?
Yeah.
Absolutely it does. It carries a partial negative and a partial positive charge. And that hydrophobic tail is going to repel water. What about a chlorine ion, which carries a negative charge? Is that going to pass freely across? No, it's not. What about oxygen gas that doesn't carry a charge?
No.
For sure. In fact, this is the primary way that our cells exchange gases. We burn up a whole bunch of oxygen and sugar and make carbon dioxide. We need to get rid of that carbon dioxide. And so diffusion allows carbon dioxide, CO2, that doesn't carry a charge, to just diffuse freely from this side of the membrane out. And when we become oxygen starved in here, when we don't have enough oxygen gas, which doesn't carry a charge, can freely diffuse back inside. So this becomes a really, really important barrier for keeping good stuff in and keeping bad stuff out. Sometimes it keeps good stuff out and bad stuff in. And we'll talk about those problems a little bit later in the semester. Okay, so that's lipid number 2, a phospholipid. Lipid number 3 that we need to talk about are steroids. So steroids are lipids because they don't dissolve in water, and they're important for communication, intercellular or between cell communication. Now, in our society, there's just this knee-jerk reaction to steroids when we say the word steroid, right? Automatically, it's bad. But they're important molecules biologically. All of us use catabolic steroids and anabolic steroids. Okay, so the foundation of all of our anabolic steroids is a molecule called cholesterol. So when we're making steroids for communication within our body, we take the cholesterol molecule and we change it up a little bit, and then it's used for communication. But cholesterol by itself has a really important function in cell membranes. Do you guys remember what a buffer is in the context of pH? Okay, so it moderates any sort of change in pH. If something's becoming a little bit too acidic, it's going to remove hydronium ion. If something's becoming a little too alkaline, it'll either introduce some hydronium ion or take up that hydroxyl group. So buffers in pH moderate changes in pH. Cholesterol does exactly the same thing in cell membranes, but with temperature. So that cell membranes don't get too hot nor do they get too cold. So if cell membranes get too hot, the membrane's going to fall apart, and cholesterol keeps that from happening. If it gets too cold, the membrane freezes, and that's also bad, and cholesterol keeps that from happening. But we can take our cholesterol and we can switch it up a little bit and make estrogen and testosterone. Now, the foundation of all anabolic steroids is the testosterone molecule. An anabolic steroid is defined as any steroid that's going to help you increase muscle mass, right? Now, there are natural amounts of testosterone in both men and women, even though it's the male sex hormone. And there are natural amounts of estrogen in both men and women, even though it's the female sex hormone. What's really interesting is guys only produce really testosterone, and females really only produce estrogen. However, there is an enzyme in our body that's able to take testosterone for guys and do some molecular magic and make estrogen out of it. Alternatively, in females, you have a similar enzyme that comes along and takes estrogen, works some molecular magic, and makes testosterone out of it. Now, there are specific times of our lives when testosterone and estrogen become incredibly important, when there are rapid biological changes occurring within our body. What are those times? Puberty, yeah. So these are the primary sex hormones that facilitate sexual maturity in both males and females. So during puberty, guys start producing a lot more testosterone, right? Which makes us bulk up in muscle mass a little bit, makes us get, unfortunately, hairy and start smelling pretty badly. For females, when you start going through puberty, you start producing more estrogen and another hormone called progesterone. And it's the combination of estrogen and progesterone that cause you to produce your secondary sexual characteristics. So your hips begin to enlarge a little bit, and you start developing breasts, and you start the ovulation cycle each month. And it's that relative amount of estrogen and progesterone that really accomplish those changes. What we can do, though, right, is we can take advantage of this naturally occurring steroid and increase performance a little bit. Enter the discussion of performance-enhancing drugs. So my question to you is, what is your opinion